So now let's switch gears here and look at electron geometry. There are two factors that define molecular structure: bond length and bond angle. Bond length, which is basically the distance between two nuclei, is dependent upon the atomic size of the two connecting atoms. So the larger the atoms, the longer the bond will be between them. So in the periodic table, the atomic size increases as you move from right to left and from top to bottom. In other words, elements at the bottom left corner of the periodic table are the largest, like francium and cesium. So let's take a look at an example here. So here we have carbon to hydrogen bond versus nitrogen to hydrogen bond versus oxygen to hydrogen bond. Since all these three atoms, carbon, nitrogen, and oxygen, are bonded to hydrogen, the bond length will be dependent upon these atoms, carbon, nitrogen versus oxygen. And so in the periodic table, the trend in atomic size is it increases from right to left. And so that means that carbon, in that case, would be the largest among these three atoms, right? So carbon is larger than nitrogen, and nitrogen is larger than oxygen. So in that case, the bond length between carbon and hydrogen would be the longest, whereas the bond length between oxygen and hydrogen, in this case, would be the shortest. And here's another example. So we have hydrogen-fluorine bond versus hydrogen to chlorine bond versus hydrogen to bromine bond. Since all three atoms are bonded to a hydrogen, we only need to compare the atomic size of fluorine, chlorine, and bromine. So in the periodic table, the trend in atomic size is that it increases from top to bottom. So that means that bromine is the largest, followed by chlorine and then fluorine. And since bromine is the largest among the three, the bond between hydrogen and bromine will be the longest, and the bond between hydrogen and fluorine would be the shortest. The geometry of a molecule can be determined by the number of electron groups surrounding the central atom. An electron group can be a lone pair, a single bond, a double bond, or even a triple bond. A central atom with multiple electron groups is stabilized by keeping these groups as far apart as possible, which reduces the repulsion between them, according to the VSEPR theory. This arrangement of electron groups introduces bond angles between the atoms. In organic chemistry, we will only focus on these three types of electron geometry: linear, trigonal planar, and tetrahedral. Any molecules with only two groups will always have a linear geometry. Three electron groups will always have trigonal planar geometry, whereas four electron groups will always have tetrahedral electron geometry. And these are the bond angles associated with the geometry. So for linear, the bond angle will be 180 degrees, trigonal planar will be 120 degrees, and a tetrahedral geometry will have 109.5 degree bond angle. Here we have an acetylene molecule in which both carbon atoms are central atoms with a triple bond. Looking at one of the central atoms, let's say this one on the left, you can see that it has two electron groups. There's a single bond here, which counts as one electron group, and there's a triple bond here, which also counts as an electron group, for a total of two electron groups. And this suggests that this molecule has a linear geometry, and the bond angle between them, between the atoms, is 180. Here we have the ball and stick model for the same molecule, which is acetylene. And as you can see here, the atoms are color-coded. We have hydrogen, carbon, that's triple bonded to another carbon, and this carbon is single bonded to a hydrogen. Make sure that you know the colors of at least the first 5 elements that's shown here. So we have carbon in black, hydrogen in white, oxygen in red, nitrogen in blue, and fluorine in yellow. Shown here is the molecule ethylene. So this is the ball and stick model of this molecule, and this is the Lewis structure for ethylene. As you can see, we have 2 carbon atoms, and both carbon atoms are central atoms. And if you look at each carbon atom, let's say this one on the left, you can see that it has a total of 3 electron groups. You have a single bond here, another single bond, and a double bond for a total of 3 electron groups. And because it has 3 electron groups, each carbon atom has a trigonal planar geometry. Since the geometry is trigonal planar, the bond angle between the atoms is 120. Shown here is the molecule methane with the chemical formula CH4. As you can see, the central carbon atom has a total of 4 single bonds, which means that it has a total of 4 electron groups. And any molecule with 4 electron groups is considered tetrahedral, with a bond angle of 109.5. This square planar arrangement shown here, with 90-degree bond angle, doesn't exist because it's not the optimum angle. The electron groups have to be as far apart as possible according to the VSEPR theory. Every time you draw a three-dimensional structure, make it a habit to include the orientation of the bonds in space. For example, a solid line, such as these two shown here, means that the bond is within the plane. Imagine a whiteboard and you lay a sheet of paper flat on the board. That paper is said to be in plane, which is parallel to the board. A wedge, like this one right here, is used for a bond that is in front of the plane, going towards you. Imagine a pencil sticking out of the board facing you. That's a wedge. A dashed line, such as this one, is used for a bond behind the plane. So make sure you practice this often now so that by the time we get to the later chapters, you'll be able to visualize three-dimensional structures a lot easier. Since molecules have three-dimensional structures, they can be rotated in many different ways which generate equal representations of the molecules. Let's pick methane as an example, which is the simplest organic molecule. Rotating this molecule produces the following similar representations as shown here. For a tetrahedral molecule, or any tetrahedral molecule, 2 bonds are always in the plane, 1 behind the plane, and 1 at the front of the plane. So when you look at these equal representations of methane, you can see that there's always 2 bonds that are in the plane, 1 bond that is a wedge, and the other one a dash wedge. If you see structures that are drawn similar to the ones shown here, these structures are actually the same. So looking at this structure on the left, you see that the wedge bond is on the right hand side, whereas the dash wedge is on the left hand side. But the structure here on the right has the normal wedge on the left and the dash wedge on the right. But in reality, these representations are equivalent. Because in reality, when you look at this ball and stick model, for example, these 2 hydrogen atoms are actually aligned. So it doesn't matter whether this is pointing towards the left or to the right. Earlier, I mentioned that a lone pair on a central atom is considered an electron group. Ammonia, for example, has this chemical formula NH3, and this is the Lewis structure. You can see that the central atom, nitrogen, has a lone pair. Ammonia has a total of 4 electron groups. It has 3 single bonds and a lone pair for a total of 4 electron groups, which gives it a tetrahedral electron geometry. But because one of these groups is a lone pair, ammonia has a trigonal pyramidal molecular geometry with bond angles less than 109.5. So the reason why the bond angle in ammonia is less than 109.5 is because of the presence of this lone pair. So non-bonding electrons require more space, and so it basically pushes some of these bonds back a little bit, which reduces the bond angle. Here's the Lewis structure for water, H2O, with oxygen as the central atom. As you can see, oxygen has a total of 4 electron groups, 2 lone pairs and 2 bonding pairs, which gives it a tetrahedral electron geometry. But because oxygen has two lone pairs, the molecular geometry is bent. So this is a bent molecule, a molecule with bent molecular shape or molecular geometry, with a bond angle also less than 109.5. In fact, the bond angle is even less for water compared to ammonia. Water, it's 105, whereas for ammonia, it's 107. And the reason being is because of the presence of two lone pairs, compared to ammonia's only single lone pair. And here's practice problem number 18. Determine the geometry around all second row elements in each compound drawn as a Lewis structure with no implied geometry. So whenever you're determining the geometry of a molecule, the first thing that you want to do is look at a central atom, a specific atom, and then count the number of electron groups around that central atom, and then determine its geometry. So for this carbon right here, this carbon has a total of 3 electron groups. Remember that an electron group can be a lone pair, a single bond, a double bond, or a triple bond. And so we have 2 single bonds here and a double bond for a total of 3 electron groups. So this carbon has 3 electron groups. And so the geometry, the electron geometry, is going to be trigonal planar. All right. What about this carbon right here? This carbon has 3 hydrogens that are single bonded onto this carbon and another single bond here. So that's a total of 4 electron groups. And any molecule with a total of 4 electron groups will have tetrahedral electron geometry. All right, and this CH3 here, this carbon is essentially the same as this carbon on the left. And so it will also have 4 electron groups and a tetrahedral electron geometry. What about this carbon? This oxygen up top, which is also a second row element. Looking at this oxygen has a total of 3 electron groups. You have 2 lone pairs and a double bond for a total of 3 electron groups. In that case, it will have a trigonal planar electron geometry. What about this second one here? Let's take a look. So we have a CH3, an oxygen, and another CH3. So this carbon right here has 3 hydrogens. That means each hydrogen is single bonded to that carbon for a total of 3 single bonds, and then another single bond between this carbon and this oxygen. So that's 4 single bonds or 4 electron groups around the carbon atom. And so it has a tetrahedral electron geometry. Now this CH3, this carbon right here, is essentially, again, the same as this carbon over here. And so it will also have 4 electron groups and a tetrahedral electron geometry. This oxygen here has 2 lone pairs, one up top and another one at the bottom, with 2 single bonds for a total of 4 electron groups. And because it has 4 electron groups, it will also have a tetrahedral electron geometry. And the third one here is amide ion. So we have an NH2. This nitrogen right here has 2 lone pairs and then 2 hydrogens bonded to it. And so each hydrogen is single bonded to the nitrogen for a total of 2 bonding pairs and 2 lone pairs. So that means it has 4 electron groups total. with a tetrahedral electron geometry. And finally, we have this one right here, a CH3 bonded to a carbon, and this carbon is triple bonded to a nitrogen with a lone pair of electrons. So this carbon here has 3 hydrogens single bonded to the carbon and another single bond to another carbon. So that's a total of 4 electron groups, which also makes it a tetrahedral molecule. This carbon right here has a triple bond and a single bond for a total of 2 electron groups, which makes it linear. And the last one is nitrogen. So this nitrogen also has 2 electron groups, a lone pair, and a triple bond. And so the electron geometry will also be linear. So here's practice problem number 19. Predict the indicated bond angles in each compound drawn as a Lewis structure with no implied geometry. So the first one here, we have 2 carbon atoms as the central atoms. And when you look at one of them, let's say this carbon on the left, it has a single bond and a triple bond. So that means it has a total of 2 electron groups. And any molecule with 2 electron groups is considered a linear molecule. And so this carbon makes a linear molecule, and it has 180-degree bond angle. So this bond angle here is 180 degrees, and this bond angle is also 180 degrees. What about this second one here? So let's look at this carbon atom, because this is going to be the central atom. And as you can see, it contains a total of 3 electron groups. So you have a double bond here, a single bond, and another single bond, for a total of 3 electron groups. And because it has 3 electron groups, the geometry is going to be trigonal planar. And any trigonal planar molecule will have 120-degree bond angle. So this bond angle right here is 120. This bond angle here is also 120. And here's another example here. So we have carbon, which is going to be the central atom here, and it contains a total of 4 single bonds, which is equal to 4 electron groups. So this carbon has 4 electron groups, and that carbon is tetrahedral. And so in that case, the bond angle between the atoms will be 109.5. And here's practice problem number 20. Using these principles of VSEPR theory, you can predict the geometry around any atom in any molecule, no matter how complex. Cytotoxin is a poisonous compound isolated from water hemlock, a highly toxic plant that grows in temperate regions in North America. Predict the geometry around the highlighted atoms in cytotoxin. All right, so let's take a look at this oxygen right here, the first one. You can see that it has 2 lone pairs and 2 single bonds. So that's a total of 4 electron groups. All right, so this oxygen right here has 4 electron groups. And because it has 4 electron groups, it will have geometry, tetrahedral geometry. All right, and this carbon right here, as you can see, has a triple bond here and a single bond for a total of 2 electron groups. And 2 electron groups equates to a linear molecule. And this carbon right here has 3 electron groups. It has 2 single bonds and 1 double bond for a total of 3 electron groups. And this carbon, in that case, is trigonal planar. All right, and what about this oxygen right here? This oxygen has 4 electron groups. And the reason why is because it has 2 lone pairs and 2 single bonds for a total of 4. So it has a tetrahedral electron geometry. And last one here is this carbon right here. It has a total of 4 single bonds and therefore 4 electron groups. This is also going to be tetrahedral.